Stats would be a tragedy. Dal suo computer. Allora, mettilo pure più qua, così non ci inciampiamo troppo. Cioè, io non inciampo.
Io l'ho sbagliato. Cosa non mettere? Questo qui, questo. Il monitor comunque in basso. Metterlo sopra, questo deve stare sotto, quando mandano giù. Vabbè che non cambia, ma... Se avete come fai tutto ordinato di riferimento?
Io non so. Allora. Are you already sharing your screen? Yes, okay. If you could check this. Right? Yes. And so you're mute, right? So I think, you have yours? So in 1 minute, I'm going to start. Okay, are you ready? Are you ready for the last session of the day? One of the last sessions of the school. I didn't know in English, but when the going gets tough, that get going. So here you are. Okay. So last and final session on statistics with the hands-on as usual. So let's follow Knut.
Yeah. Hello, everyone. So as Marco said, you really need to now dig deep into the well of whatever many topics you have available to you, because today we're going to talk about confidence intervals. However, before that, I'm just going to quickly scroll through. I uploaded an example solution for most of the exercises from yesterday. So yesterday we looked at likelihood optimization, confidence interval. Exercise 2 didn't have confidence interval per se, but in particular also asymptoticity checks to check when do the assumptions that allow us to use these different asymptotic forms, when do they fail and when do they hold? So the exercise set started, let's see, I can move this a little bit, and then we'll go. So the exercise set started with some preliminaries just on the fact that you have to make sure to offer your function in the correct form to the minimizer. But once you've done this, you should all have been allowed to run this with success and get some nice optima. If you have linearity, I think it's nice because you can more easily flexibly change parameter bounds on the go. But that's more if you know that you will do this for some hundreds of thousands of times. If not, I think the scipy.stats works great, and it worked for actual published results also. And then we have, just a little plot of what these likely surfaces might look like. You have some two parameters, and you might have some correlations that necessitates that you don't just look at the projection along here, but that you actually walk along the minimum, which is what we call profiling. And so we had some proposal likelihood that we were supposed to write. And then to write these, we have built-in functions to make a Poisson with a known background. And we can either generate or select some sort of data and observe what the best fit is for these guys. And we can do this for many loops. In that case, you get a lot of complaints because it doesn't like that you have set it to infinity below s equals 0. That's fine. You can either pass a bound to the minimizer, in which case the minimizer itself will be clever and never go there. Or you can live with these warnings, just take them off somewhere. Just make sure to not write them all to a .log file. That will then just be a lot of useless text. At the bottom, there is a nice plot, which should have been in a separate cell if I were clever. Let's do this.
How many loops did you ask?
Not so many. Hundreds, but then of course inside it's going to loop many more times to do the actual asking here. How fun. We have then some distribution of the best fit signal. That's in itself not that informative in particular here because the actual true signal was rather small. As true was 3.2, so it could be if you squint a lot, you might say I'm happy with this, that it at least doesn't all goes to 0, right? It has some bimodal distribution here where it likes to go to the true value some parts of the time. And then we did some hypothesis testing. This is always good. And you could see that you have different distributions if you have different underlying hypotheses. This means that this test statistic is able to distinguish these two hypotheses, which is what we want. And with asymptotics, you can check now how good is H0, right? You can test these different hypotheses. You can plot here. So this is here if you're doing discovery, which means that you're testing the hypothesis there is 0 signal. You can see here a little bit hard against the orange, but there is a curve or a histogram underneath here that corresponds to the expectation from Chernov's theorem, which is that if you're at a boundary, but that's the only thing that is a problem with asymptotics, then your distribution will be half chi-squared plus half delta function at 0. While if you have then signal equals 10, then you have many more of these guys are going to go out to positive values of the likelihood ratio, which means that you could start excluding some of them, and you would have some power to distinguish between them. I wrote one oopsie here. This below said H1 equals, H1 was B equals 5, it should have been S equals 5. I hope those of you who got there either complained to me or found out that it would be better to set the signal to something. And here you see this is now quite discrete. Now we turn down the background and the signal values, and then you have these steps. That means that you will not have correct coverage for all of these values. And you can then, if you can't trust Wilks theorem, you can still trust the power of toy Monte Carlos. And so you can just compute, this is a nice function, scipy.stats.percentile with score, highly recommend it, which allows you to compute percentiles of one array as percentiles of the other. And this means that just with this one line of code, you compute with the percentile of all these orange toy MCs as percentiles of this guy here. So that means that if you go out here, say you're over here, it's just going to say, oh, there's no toy MCs out here, so my percentile is in the 0 P value. Well, if you're up here, for example, it's going to look, oops, I'm at 10 or 15 roughly, and that means my P value is roughly 10 to the minus 5 or something like this. And so here we see that we even get a power, and that power is great. We get almost 90% power to reject H0. With nuisance parameters, it becomes only a slight bit more complicated. You add a check that the background is greater than 0. And you now also need, at least if you're using SciPy optimizer, you need this extra little wiggle, which is that you define a separate function to minimize when you have set one value to a fixed value, or you set one parameter to a fixed value. We'll look at this today again from here on outwards, so you'll get to look at these also for today's exercises. But what you do then when you profile is you generate some values, you find your best fit, you read out your best fit, and then you have a number of signals that you're testing, an array called S-tests here. And for all of those, you minimize this conditional likelihood, so the likelihood where only the background is free to vary, while you set S-test to some fixed value. And then you store the hats and the likelihoods or log likelihoods for those guys also. And then you compute the log likelihood ratio. Here I just computed some examples, some random examples of how this looks for a couple of times the examples. And you see in some cases your best fit is very, very, very 0. In some cases your best fit is still 0, but it's not that extremely 0. So these are sort of degrees of under-fluctuation with respect to your background. Well, in other cases, your best fit is, half or 3 or some other nice value. And we can check the distribution here. Oops. Do we have the nice plot? Here we have S hat, here we have the estimated B. So you see here that that hat is a little bit shifted upwards, right? Because we're testing a lot of signals that are bigger than the signal that we actually have. And we see that now that once we have also the background near a boundary, then Chernov's theorem doesn't hold anymore, right? So we can't just assume that we're at one boundary. We either have to assume that we're at 2 boundaries, or we're now only near one of the boundaries, so we have to time C it out, or we have to use higher order asymptotics. So here we went, or at least I went through and did the same thing when I set the hat to close to the boundary, or in this which case you can see actually it looks like somewhere between half chi-squared and quarter chi-squared if you're at the boundary of background or of the background also. Okay. And so today, once we're done with the lecture, we'll look at this again in the context of confidence intervals, which are really just repeated hypotheses testing. And so then we'll do profile construction to make a nice confidence interval, also using the same likelihood. Good. Questions on the exercise sessions from last time, or otherwise we continue to the lecture? No?
Seems not. So
Good. Then I will move over to this one and press play. And we're still sharing. Yes, everything is shared where it should be shared. Here's your pointer up and down. Right, so we just went through the exercise sets from last time. And yesterday we discussed a lot about example analysis, which discussed, what kind of statistical models in terms of likelihoods we have for different experiments. We discussed profile likelihoods, and we took a lot of time to discuss these asymptotic distributions, both because it's important to know when they fail, and because they can be very, very useful in many cases if they don't fail, and they often don't fail. They perhaps fail more often for us who are doing rare event searches, but still for us, if you're doing some spectral fits to find high energy ER lines in xenon or other things, it still is quite common that you can assume these guys and save yourself a lot of time. And we discussed look elsewhere effect and other sources of experimental bias. That means that you have to be careful when you run these. Even beyond getting this guy right, you have to make sure that the process of your analysis avoids possible sources of biases. And so for today, we have a rather short agenda, but these are going to be all big topics, which first of all is frequentist confidence intervals. Then we'll continue with the profile construction, which is the special case of frequentist confidence intervals. And then lastly, I'll just point you guys to 2 tools that you can have a look at if you want to get more into this, if you want like more detailed tutorials on how to do this for quite a realistic example of liquid xenon TPC likelihood. Then we have some proposals here. Good. So again, we don't escape profiling likelihoods so easily, so we'll come back to this again. So we seldom have completely specified hypotheses. And so we want to profile out here. So again, here we have signal expectation and background, and we have a likelihood that tells us that the most likely case is here. But as you increase signal expectation, the most likely one, given that signal expectation, goes down to accommodate the extra signal. And we have this notation with the hat for the conditional best fit and with the S hat, theta hat for the best fit. Good. So confidence intervals, we always, much more important than being able to have an unbiased estimator for something is being able to say how certain are we about something, right? It's the first and most important part of scientific honesty, I think, is to be able to say what uncertainty do we have about this thing we're saying. And so this should be always our main output, or we should at least think of it as part of our main output, is us quantifying the uncertainty with which we say we know something. And so within the frequencies paradigm, we do this with what are called confidence intervals. These are very similar to hypotheses tests in that they're defined in a way to say that some portion of the time we will not reject H0, or some portion of the time we will not reject a certain signal. And so there is a certain probability of false rejection. These don't need to be one-dimensional, although they very often are presented this way. So this is one cross-section, and they're all just lines. And they say we can't exclude signals down here. But they can also quite often be 2-dimensional. And in principle, many of them are, these are also projections of having profiled out many of these uncertainties or set them to some base value. So this is an example for the liquid xenon likelihood, where you have the WIMP nucleon cross-section, and here you have the local circular velocity, so the velocity with which dark matter goes around the galaxy. And as you change this, then you move more or less of the dark matter above the threshold of the detector. And so you have some 2D uncertainty confidence interval for this, if you want to take also this uncertainty into account, sort of on equal level with the WIMP nucleon cross-section.
So
yes,
maybe on this point, if I may, on the top plot, probably it's helpful to clarify that even that is a one-dimensional
yes,
approach.
this is
because we
a
really
very good point. Yes. So they're 2-dimensional in the sense that we have 2 axes here, but the limits here are 1-dimensional. The limits here are only saying for 400 GeV mass WIMP, there is an upper limit here. And then we have a separate hypothesis test, or we have a separate upper limit here for 200, for 300, for 400, etc. That was a choice we made. We could have done it differently. We could have done sort of unified blobs of 2-dimensional confidence intervals here. They would have often looked the same as these guys, but they would have sometimes looked surprisingly not like these guys in ways that made them difficult to interpret, I think. And so that's why currently, or not just because I think it, but because of those arguments about them being difficult to interpret, is why we're not currently making them in these 2-dimensional spaces. Once we discover dark matter, it will be very common to see 2D blobs. You might have seen some Doppler blobs up here before. If you have a discovery, people start getting interested in, what kind of combination of mass and cross-section does this correspond to? And we would then go and publish some little blobs here for also if the Lucino TPCs discover something. However, for as long as there are only upper limits, as long as we are below 3 sigma at the moment, we will only publish these sort of per mass upper limits.
Yeah, so basically they are not two simultaneously fitted three parameters.
Yeah.
The mass is fixed, is assumed, and at that mass we interpret the unit on the cross section.
Ask me during dinner how this connects to the look elsewhere effect.
Right.
In any ways, so upper limits, confidence intervals. Sometimes you're asked, well, what's the uncertainty of this upper limit? No, we should have an error bar. But the answer is the upper limit is our error bar. This is very important to say that upper limits are not themselves best fits. They're not themselves point estimates. Almost always our best fit is, okay, minus infinity on log scale. If we have a sim log down here, it's at exactly 0. Or sometimes we have a small non-zero best fit. But that's almost all dark matter direct detection results have been like this. They're either 0 minus 0 plus upper limits, or they're epsilon minus epsilon plus upper limits. So it means that, which is also a point I would encourage you to never think of upper limits as something that doesn't have a lower bound. So always confidence intervals have two sides. It's just that sometimes that side goes down to minus infinity. It becomes much, much, much easier to think about these if you never forget about this lower edge of your upper limit. And then these Brazil bands you will often see when results are reported. These are also not uncertainty bands for the upper limit. These Brazil bands show your a priori expectation of where the limit should end up, given your model, right? But not given your data. So it means that before you unblind it, or perhaps with some parameters fit to after you're blinded, but not taking your data into account, where would you expect this upper limit to happen? So here's an example for Xin and Anton. We expected our limit to be here at the sensitivity, which is between the dark and the light green. But in fact, when we unblinded, we saw that we had what is called an upwards fluctuation, which is when your limit goes above what you expect. Oh, it's quite moderate. It's 1 sigma. Going back to what, counting sigmas, this just means that it's the 85th percentile of upper limits. But it is, this is all that it means. And don't interpret these guys as error bars. They can be used to more give you an impression of was this within the expected range of results, or is this very surprising? And also this is if you now take, back. If you now look at this plot and you look at it in a slice here, if you choose some certain mass and look at a slice, this is how it looks, very cool. These are our likelihood ratios, log likelihood ratios here. And they're a function of both the winged nucleon cross-section here, or if you want to reformulate it, they can be a function of the estimated expected number of winged events here. And so you see here, you can make TMCs, zoops, or you can check your actual data. And then you have here in dashes, you have the asymptotic result. And here you will see afterwards in the profile construction that we have also this non-asymptotic result. But the important part is down here. Here you see how these Brazil bands are made. So this is the cumulative distribution of upper limits, given our null hypothesis, and just using TMCs. So we just redid our experiment on a computer some thousands of times. And we saw how many of these upper limits are below this value or this value or this value. And then the Brazil band here is just -1 sigma. That's 0.15 something in the normal distribution. And then here, the middle of the Brazil band is the median. So that's where the median upper limit is. And then the upper edge of the 1 sigma band for the Brazil band is here up at 0.85. And then you have the 2 sigma band for the same 0.2 sigma. But how do we make them, and what do we care about when we make these confidence intervals? So I said before that we care about them in terms of false rejection. However, in normal chatting about these upper limits, they're almost always formulated instead in terms of coverage, which is 1 minus false acceptance. That is, how many times do you contain your true parameter within the confidence interval you make? And so what you do then is you do a lot of TMCs, and you recompute your upper limit. This is how we're going to compute our upper limits with the profile likelihood. And then you find your upper and lower limit. And here you see you have some parameter that you want to estimate. And you count how many times the upper limit is beyond containing that true parameter and where it contains it. And the coverage is how many times does the confidence interval that we construct, based on our method, whatever that method is, how many times does that confidence interval contain the true parameter, given some true parameter? And the goal of our frequentist confidence interval construction is that we should be able to make a construction that can guarantee that we have this coverage, that we have the coverage that we want for any true value of signal. So not just testing this guy, but testing every single possible value of mu. We should be able to guarantee that we have this thing that is called coverage for all of them. So how do we do that? Well, we do that with initially with something that is called Niemann constructions. Niemann constructions look at, again, we check for each signal value s. And we find the distribution of the test statistic. We choose some test statistic that is good to test what we want to find out. And we find the distribution of this test statistic. And then we find these two lines here, which is the line x down and x up, between which x occurs the coverage amount of times, or the confidence level amount of time. Right, so you do that for one signal here, and then you invert them to find, then you look up here when you search in certain value, you can invert these lines to find your confidence interval here. Now this is hard to see with one, so let's go through this in more detail. So here is some example where you have some model, some statistical model that depends on some signal parameter and that predicts some test statistic or some estimator here. And you see that our model says that these are Gaussian distributed, but they have some different width depending and some different mean depending on what the signal parameter is. So what you do then is for every single value of the true parameter, you construct these here and you say, I want, in this case, it's 90%. So I want 90% of my probability density, or 90% of my probability. So integrated of the probability density. I want 90% containing this, containing this, containing this, and containing this within these dark blue areas. And then you do it for all of them along. And that gives you this Niemann construction band here. And this Niemann construction band is what will allow you then to compute upper limits, because you can invert this. Once you have observed something, you observe now this value of x. You can invert this to say, okay, my confidence interval for s is between this edge here, which is the lower edge of this Niemann construction, up to the upper edge here. And it takes some time to think about why it is that this thing exactly guarantees that you'll have coverage. But think about this again. If you're here, if you're below here, right? Now you say 90% of my probability is here, then it appearing out here will be less likely than 90%. So this, you don't, if you were looking at this signal here, you wouldn't have coverage. But if you're looking in here, then you say, okay, if I'm at -1, then in 90% of the cases, x will be between here and here. And if x is between here and here, then -1 is contained in this region. So then I have coverage for -1. And the same, if I look at -0.75. Okay, x is between here and here. So in 90% of the cases, x happens between here. And in all those cases where x happens between here and here, this line here will cover -0.75. So for all of these guys, we can make that argument. And that means that for all of these guys, we have coverage. And that is the Niemann construction. And that's what we're going to use to compute frequentist confidence intervals. Sometimes this happens almost automatically and you don't need to think about it. In particular, if you're doing Gaussian confidence intervals with a fixed standard deviation, they're just straight lines. And you don't even have to make the construction. You can just add and subtract 1.63 or 1.64 sigma to get a 90% confidence interval. And you probably didn't even notice you were doing a Niemann construction. But in general, you have to go through this. You have to go through every single signal and make sure you have the right belt for that one to make sure it's going to be included 90% of the cases. However, or actually a useful note here is that because this coverage is concerned with the integrated probability rather than a probability density, that means it's much easier to transform confidence intervals than it is to convert point estimates. In general, it's not true that your point estimate for x, if you just square that will not necessarily be an unbiased estimator for x squared. However, for confidence limits, because you're looking at the density between these limits, you can transform them with any monotonic transformation and still get a valid confidence interval. So that's very useful. That's another reason to love confidence intervals. However, one problematic thing, if you're dealing with counting, is that it's often quite hard to actually guarantee that you have exactly 90% between. You know, if you have a Poisson distribution with some certain expectation value, you only have those discrete observations, so you're not going to be able to say between this number of events and that number of events, I'm going to have exactly 90% of my outcomes. So either, or in almost all cases, we err on what is called, what is called overcoverage here, which means that you just construct it to have at least 90%, and then you're going to have, this is a plot of the coverage versus the true signal, and you see you have this fun, weird, bouncy thing. Other people have proposed that you can say, okay, if I can't have 90% within this region, I can roll a random number and say, okay, if I'm just at the edges, I will only take a certain fraction of those outcomes to mean that I'm inside, and a certain fraction that means that I'm outside. So you would not only be measuring something in physics, you would also be rolling a dice to say whether you're going to include or exclude a certain value. I think very, very, very few physicists enjoy that, although I think it would be fun to publish such a paper at least once. But in general, you're going to do this. You're just going to say, okay, at least 90%. And then this can often be irksome to get this step exactly right. You know, imagine going through this and say, okay, I have exactly this observation. Did I make sure to make this step right here, or do I have an off by one error? Do a small toy test if you're unsure, you know, because this is very common that you get these steps wrong. Also, a note is, so far, I have not completely determined the Niemann construction for you guys. Now, you could move these guys to say, okay, perhaps I want all of that 90% integral over to the left side, or I want all of that probability all the way up to the right side, or I have some other special rule of preference that means I want to have all of them at some point or the other. And all of those would have coverage, right? You could even do some crazy thing where you say, I want to include all of my probability except where I have the most probability. Now, that would be a bad confidence interval in the sense that it wouldn't give you all the information that you want about the parameter, but it would be a valid confidence interval in the sense of frequentist statistics. However, in almost all cases, you either have upper limits, lower limits, or you make something that is central around the best fit. However, there is one extra, and perhaps the most common of all in our field, and that is that we choose our bounds in such a way that it provides both upper limits and confidence intervals depending on what the result is. And the reason why we like this is because we want to avoid something that is called flip-flopping, which is that if you have one Niemann construction, you have coverage. However, if you have two Niemann constructions, you no longer have coverage if you're switching between them based on what your data says. So this is an example here. These are Niemann constructions for a Gaussian observation. Here you have your observable and your true parameter. And here you see if your signal is below 3 sigma here, or if you interpret these as sigmas, if your signal is below here, you're just going to set an upper limit. Well, if it's above here, you say, oh, we saw something that is definitely in excess at least, and people will know where that excess is, so we should publish a two-sided confidence interval. And in those cases, when you're switching between these two, you actually get under coverage, because the coverage doesn't work in this direction, right? It works in this direction here. And now because you made the switch, now you have less than 90% across here for some certain signals. And so you get this under coverage here. That is exactly what we want to avoid. And there's actually a similar case here, which is, you know, an even more subtle case, which is even if your experiment reruns your observation, only if it looks like an outlier, right? If you say, I want to rerun my experiment if it looks like an outlier, if I have like more than a couple of sigmas deviation in both sides, I'm going to rerun. And I'm going to rerun with a better experiment. So you see here, the blue one here represents the better experiment with tighter constraints. And even in that case, you will get this both under and over coverage here. So in general, it's important that, you know, once you've done, you should commit to these decisions before you do an unblinding. You should commit to these kind of decisions before you actually look at the data. Otherwise, you will always wonder with yourself, you know, did I choose one or the other based on what I saw in the data? And the way to solve this is to have just one Niemann construction. And in particular, you want one Niemann construction that either provides upper limits or provide two-sided confidence intervals based on the data. And the vastly most popular version of this is what is called the Feldman-Cousins intervals, or unified confidence intervals. In this case, you see here, so here we have a physical boundary. We say we can't have signals below 0. And this is the case where you will get flip-flopping, right? If we were okay with setting confidence intervals at -50 for the wave cross-section, then we wouldn't need to flip-flop between upper limits and two-sided intervals. But in this case, you can see here, okay, if I measure -2 here for this S hat, then I'm just going to set an upper limit, right? My confidence interval is going to be between 0 and this upper edge of this NEMA construction, which is the Feldman-Cousins construction. If I go up here, if I measure the median result, then I'm also just going to get an upper limit. If I get a higher value here, if I have an upwards fluctuation, then I'm going to get a two-sided confidence interval here. If I measure S hat equals 2, then my confidence interval is going to be something like 0.5 to 5 or something like this, which is great. No, that's exactly what we want. The problem is the way to do this is to include parts of this in your NEMA construction ordered by the profile likelihood ratio, or the way the Feldman-Cousins described it, only based on the likelihood ratio. So you choose here, you choose to include first, this here in black is the highest ordering ratio. It's the best fit to the hypothesis. And you see here, you start with this, and then you start adding more and more out from the sides of this best fit parameter. Audience participation question. Can someone guess, if I say this is a 90% confidence interval, can anybody guess what p-value this guy lifts up from 0 at? Right, it turns out that this has a certain connection to the coverage, which means that you lift up at a very specific point. Remember that you want exact coverage at 0. Okay, so exact coverage at 0 means that 90% of the cases, S hat will be between here and here, right? Or between -infinity and here. So that means by process of elimination that 10% of cases are out here. So 10% of cases are equally or more extreme than the null hypotheses. You know, we're testing out the null hypothesis. So the Feldman-Cousins intervals lifts up at exactly 1 minus CL. So your p-value is 0.1 exactly when your Feldman-Cousins interval lifts up. Some people or some collaborations even don't think this is conservative enough, so they will add an extra fillet here to say, okay, we're not going to publish two-sided confidence intervals until we have a much bigger upward fluctuation than p-value of 0.1. But that will then get you over coverage, right? Because you've added more to this construction that gives you exact coverage. Okay, making this can be a bit of a hassle. Like making this thing, I had to make a big 2D scan over likelihoods here for different S hats and S. However, it turns out to be a much more tidy way of doing it, and it turns out, you know, frankly, at least for me, it's the easiest way to do confidence intervals if you have to do them with TOMCs, which is what is called the profile construction, which is the combination of unified intervals with nuisance parameters. A warning is that this means you're no longer guaranteed coverage. If you have nuisance parameters, they can change your distributions, which means they can also change your distributions of your test statistic. And so your NEMA construction, that you very carefully constructed, it could be that these boundaries are slightly different based on some nuisance parameters, in which case you won't have exact coverage. However, in practice, it turns out to be reasonably robust for most cases. You should test if some of your nuisance parameters have very big effects on the signal, or very big effects on the signal-like background. Then you should at least start worrying that this could fail. But in practice, it almost always works. And the way you do the profile construction is exactly by repeated hypotheses tests like we did yesterday. That is, you look here, and these are now sideways to how we've usually been looking at them. But here we have mu signal here. This is the true value of mu signal. Here we have alpha, the fraction of TOMCs below a certain value. And here we have the 2 times log likelihood ratio here, that is testing a certain hypothesis. And the gray here are thousands and thousands of TOMCs that I've drawn from the hypothesis that mu equals 0. And I've drawn them and found that this is the distribution, right? This is the survival probability. This is the p-value as a function of the likelihood ratio, right? This is the probability that this likelihood ratio here which is 1.4 or something, will be at or below, or it will be equally or more extreme since it's p-value, it goes this way. And so it's about, yeah, 0.15 or something. So this one is not excluded. No, and this is the likelihood ratio we measure with this. No, these two axes are the same. So we go a couple of steps further. Now I've done multiple term C's here for each of these steps in true value of mu signal. And for each of them, you have a curve here. No, that's based on the term C's that says, this is how to convert your log likelihood ratio to p-values for this true signal. Right, so you compute your likelihood and you compute your p-value for that likelihood side by side. And then you do this for all the different mu signals, whoop, out. So fun. And you see here you have your likelihood ratio, no, that you're testing. Here you have the 90% thresholds. Those are these guys, right? You went along here. Let's do it one more time. See here, these are the 90% thresholds. These are these guys here that go in magenta. While the blue is the likelihood ratio that we compute for the actual data set. And now we've gone through there and we've done these repeated hypotheses tests. And with these repeated hypothesis tests, we've checked we can't exclude signal of 0. We can't exclude signal of 1. We can't exclude signal of 2, all the way up to, say, 12 or something. And crucially, we've done all those repeated hypotheses tests based on the likelihood ratio, based on the ordering parameter in the Feldman-Cousins construction, which means that we did exactly what the Feldman-Cousins construction told us to do, which is to start with the best log likelihood ratio, right? Start here, and definitely include that, and then include outwards until you're at 90%, right? So that's what these guys are saying. You know, start at the best and include outwards until you're at p-value of 0.1. Let's go back. Oops, back is the other way. So here, so now instead of having this be 2D, right, because here the likelihood ratio goes both ways here, now we're essentially just looking at this with the likelihood ratio on this axis and just start saying 0 is the best, higher values are the worst, and we just exclude things that are beyond the 90th percentile of the log likelihood ratio value. Right, which is here. Oops. These are the curves for where 90% of the log likelihood ratio is for these different hypotheses, right? So these are, if you will, this is the threshold for 90% of each of these hypotheses' log likelihood ratio distribution. Okay, hands up if you're still confused. Very fair. Does anyone want to hazard a question to specify why they're confused, or should I keep talking about it? Free hand. Yes, so.
Question, what it increases first, the yellow line, I mean the purple line. The purple line first increases and then plateaus. Is that normal? I would think that it would increase like monotonically or like go up and down.
So this guy here, so first of all, this is because I stopped doing prime C's after a certain point. But second of all, this is asymptoticity. Asymptoticity is if you have really big signals, that means you have really big, so now you're not testing s equals 0. Now you're testing s equals 20. So you have really quite a few signal-like events in your distribution. And so you've reached this asymptoticity, right? So you see this is 2.7. You'll see this when you do the exercises, that 2.7 is the 90% threshold for log likelihood ratios. So this is exactly how it looks like as you approach asymptoticity. Is almost always, you know, if you have a Gaussian, it's not going to overshoot. But if you have a Poisson or something that is like a Poisson, that is typically going to start. It's going to start at half chi-squared, right? That is also Chernov's theorem. It says it's going to start at half chi-squared. It might not be exactly that because we're looking at a more difficult likelihood than something ideal, but it's going to start around 1.6, which is half the chi-squared for 0.1. And then it's going to at some point approach 2.7 out here if you don't have other sources of non-asymptoticity. And the path you take there is very often this kind of whoop, overshoot and then back.
All right, so if it were to go keep going up, then that means that something went wrong, right? So
yes, that would work. It either means something went wrong with your minimization or something, or it's a sign that something is wrong with your assumptions that everything else about this behaves asymptotically. In particular, I've seen before that this has happened if you have other nuisance parameters, like imagine some signal efficiency that is being driven to 0 because you're very uncertain about the signal efficiency. And so this thing just goes down to 0 as you start pushing up the signal. And you have something where you have multiple boundaries and perhaps you're not quite at the boundary. And then you're in trouble if you don't then do two-dimensional confidence intervals, because you can't assume that this profile likelihood will get to the right result.
Right, thank you.
Okay, so once more, for good luck. So the NEMA construction says include the bits with the highest log likelihood ratio first, the darkest black parts here, and include outwards, which means includes upwards in log likelihood ratio, which means worse agreement, right? If you remember the curve, upwards means that it's worse in the middle where it's 0, that's the best fit, right? So we include from 0, which is this black line here, outwards until we have 90% of the probability covered. And how do we find out when we have 90% of the probability covered? We run time Cs for each signal that says what is the distribution of our ordering statistics here, the log likelihood ratio. And so here we've done this for 1, we've run a time C, and that allows you to go from a log likelihood ratio that says, okay, this is in the 10th, the magenta here shows the 10th percentile of these guys. So here you say, okay, the 10th percentile of this is at 1.4 or something. And that means that if you were to test the hypothesis that S equals 0 at a confidence level of 0.1, or sorry, confidence level of 0.9, alpha of 0.1, then you would say, okay, I can't reject this because my likelihood ratio is within the 90th percentile quantile of the log likelihood ratio distribution. You do this for all the different signals, right? Now you've checked different signals now, and because your best fit signal is non-zero, at the start the likelihood ratio goes down. It's even better fitted. It's even less excluded. And you're comparing with this 0.1 percentile of the log likelihood ratio distribution, and you think, okay, fine, it's never going to get there. But then you start adding more and more signal, and now it's getting more disagreement. It says, no, you can't have this much signal in. While again, these guys, you see here, all these lines also start to agree more and more. This is the asymptotic limit here. They don't quite agree in the far quantiles, but in the near quantiles, these guys are starting to converge. And this is saying that in 90% of cases, for signals that are roughly like 10 or above, then this 90% quantile is always around 2.7. So your upper limit is always the intersection with this 2.7 if it's above 10. Okay, so we're going to do this also in the exercises. If someone have more questions right now, lift your hand. Otherwise, we're going to continue with the slides. 3, 2, 1, go. So again, we have a threshold. If and when our log likelihood ratio exceeds that threshold, which means that for that signal, our hypothesis test excludes that signal. So if and when it exceeds it, that's when we exclude. Or for that matter, if you have two, if you have something that went whoop, then you would exclude both here and here, and you would say, above here we exclude, and below here we exclude. In here we have the guys that are not rejected by the hypothesis test. And so again, the confidence interval is a union of all signal models we cannot exclude. If you had a weird likelihood, that went up and down and up and down and up and down, that would be fine. Again, you're doing hypothesis tests for each signal. When you're doing that hypothesis test, you only care about that signal. And even if you then have a weird likelihood, you would still just have the confidence interval being the union of all signal models we cannot exclude, which is all the regions where the log likelihood ratio curve is below the threshold curve that you computed, either by assuming asymptotics or that you computed using time Cs for each of those signals. One note on nuisance parameters again. No, you're computing these time Cs, right? Here you can also see the progress towards asymptoticity. Here you have the darkest black is the lowest signal expectation. And then as you increase the signal expectation, this is how the log likelihood ratio distribution moves up towards a 1 chi-squared distribution here, which is the asymptotic limit. This you typically do, right? You compute time Cs to compute these distributions, right? For every one of these curves, some 6,000 Cs of xenon 1 ton were produced, were fitted, and you found the log likelihood ratio testing, say, with this guy here, for a signal of 2, you tested the hypothesis of signal 2 6,000 times, 4 Cs. And then you put them into these distributions. Now, which nuisance parameters did I put into these guys to start with? In general, you put in the best fit, or your best fit before unwinding for these guys. If you think your distribution or if you think your method is resistant enough against usage parameters, that's good, you're done. However, you should try to test. You could always check, I don't think there's a firm procedure for checking it, but you could, for example, fix them to best fit values and be certain you're not using the true values. You could randomize them according to the uncertainty. But I think the best is to just check how vulnerable you are to these moments. So this is an example from Xenon 1 again, where we had a parameter that was called the signal-like mismodeling term here. And we checked here, this was the one that was used for our NEMA construction, right? Which was we had certain signals and we had the true value of this being set to 0, which was what we assumed. But here we also checked, what is the coverage if we are wrong? And this value is really, okay, 0.012 doesn't seem so much, but this is like 5 sigma away from the best fit that we have, and also the other way around. And we checked that the coverage, if you were to average the coverage across here and average the coverage across here, it was like plus minus a couple of percentage points in coverage, and we were happy with that, and we could report it in the paper. Okay. NEMA constructions, profile constructions. What if you don't have a background distribution? This is quite often the case also. So there are procedures for doing frequentist confidence intervals without a background distribution and without a likelihood. In those cases, you can use what is called optimum interval methods, for example, which are quite common, which is, in that case, you assume all your background or all your events are from signal and then say, okay, what is the maximum signal size that could have caused this whole signal distribution? Now, that would just give you a counting experiment, right? It would give you a counting experiment and you would have perhaps hundreds of these events and you would get a very, very bad upper limit. What it turns out that you can do instead is you can say, what is the maximum gap here in terms of expected signal? So what is the largest gap where I didn't see any events, where I would have expected to see events given my signal distribution? Right, so if this is your signal distribution, you look here, okay, I mean, the PDF is high here, but this is a very small gap, so we don't expect so many signal events here. But this is a big guy here with a lot of area, and here we should have seen some signal if the signal hypothesis really were true. And so this optimal interval and max gap method is about being able to convert, finding this maximum gap and how much signal should have been there if the signal hypothesis is true, to the actual upper limit. And that allows you to do better than just counting because you're taking the spectral information into account. You're essentially looking for the most background-free region here, because you're assuming actually most of this is background. But you're taking into account the fact that if this was all signal, then you would have had a certain trial factor, right? If this were all signal, there would have been a probability for this guy to be this big. There would have been a probability to expect, say, if this thing normalizes to, say, 10 signal events or something, and this says, oh, I expected 4 of them in this gap and I saw 0. And there has to be a probability, right? Even if all of them were signal, it has to be a probability that the largest gap between 2 of those signal events was an expectation of 4. And that's exactly what these curves from Yellen and others are. That allows you to convert from this guy to that guy. There's a nice paper. There are online codes to do this for you. And these give good confidence intervals if you can't characterize your background further. If you can add backgrounds here, then you're doing even better.
So basically here you don't know your background model. Basically. This
Right.
is the assumption, right? This is what you do when you cannot have a proper model.
Exactly.
And so you attribute all the events to the signal, and this is the worst case for it, at least for the upper limit.
Right. Yes.
Right?
Yes.
You are paying the price
Right.
of not having the
Yeah.
background model.
And in particular, you can't do any kind of discovery with this, right? You're only testing upper limits. You're only saying, right. But it is possible, sort of, by thinking of them as signal events in a special way, which is in a way that both consider the expectation values and the shape, then you can get better upper limits than if you were to just look at the counting rate of the presumably almost background full or presumably background dominated distribution that you couldn't distinguish. Good. We are almost at the end, but we have a full exercise session afterwards, so that's no problem at all. 2 notes on Bayesian methods. So now we've almost all talked about, given each particular signal, what is the probability to reject? That's the frequentist way of thinking, is that you want You want fixed probabilities for every possible value of signal. However, if you're Bayesian, don't despair. You can make confidence intervals as well as anyone, which are called credible intervals. Now, one side on Bayesianism, you can consistently interpret probability as degree of belief. The price you pay for that is you have to input your degree of prior belief to this. You have to input a prior to be able to use these Bayesian methods. You can quibble about these priors. You can say, I really have an objective prior, I used a flat prior, and that's not that vulnerable to these mismodelings, which is fine, but it's definitely it's a choice, and it's a choice you have to specify in your paper, which means that you, at least for particle physics, it's not been so popular. For cosmology, you've seen this almost all everywhere. And in particular, Bayesianism, because it's about degree of belief, the credible intervals from Bayesianism, or in general results from Bayesian methods, are going to say something about your degree of belief in some physical model, in the mass of the WIMP or in the cross-section of the WIMP. This is also the case when you get to credible intervals. Bayesian credible intervals express where the experimenter has a certain total amount of posterior belief. So when you were to do some Bayesian confidence or credible interval, I mix them, but you shouldn't. You find a region that integrates the posterior, right? So the posterior is the main object of Bayesian analysis, which is your degree of belief having incorporated the data from the experiment, which is using Bayes' theorem, just being the important word here, because of course it can be as complicated as you could imagine. If you have many nuisance parameters, if you have complicated models, the models are hard to define. But once you've done that definition, you have some posterior, you have some degree of posterior belief, and your credible interval is a region that integrates this posterior up to the required credible interval size. These results, Bayesian frequentist results, will converge in the limit of infinite data if you haven't done something very extreme like setting your prior to 0 at the correct value. But in the meantime, it's not necessarily guaranteed. And there is no like purely Bayesian analog to coverage. Many people still check their coverage of Bayesian credible intervals, and sometimes they have good coverage properties. But it's not something that is inherent to the method. And in fact, it's a little bit unfair to ask them to have coverage when the method never ever promises that it would have it. You know, that's more, if you're used to frequentist intervals and you want to have both, then you would also ask of these Bayesian intervals to have coverage. And so there are great online tools to do Bayesian confidence intervals or Bayesian analysis and Bayesian credible intervals and Bayesian analysis in general. EMC is a very standard way of sampling these posteriors and getting out the posterior density. So this is somewhere we can look if you're interested in dipping your toe into this. Otherwise, I want to just give one slide on something that has become a little bit pop in at least the liquid xenon community, which is that you can make these very advanced sort of completely specified likelihoods that are not just approximations with some templates, you know, with some TOMC generations, but they are like fully saying, I have a certain probability of detecting a photon if that photon hit the wall, or sorry, no, that's not true. If that photon was detected, then it has a certain probability to be reconstructed as an S1. And you can write out all these probabilities in an efficient matrix language in such a way that you can give out a probability to observe that event at that time, in that position, with that S1, with that S2, which is quite nice. But this inherently requires a model to be very highly dimensional, no, 6-dimensional. And it turns out that for some technical reasons, reducing the dimensionality of this isn't without significant computational cost. It also induces quite a bit of computation time for a single best fit because it's a quite complicated model, which is not a problem for a best fit, but so far it's been a challenge for TOMC estimates. But this, on the other hand, it does promise that you'll get a lot of extra freedom in your model to add more analysis dimension. You can inherently model the full spatial and energy distribution of your signal. Also, a small advertisement for the current Xenon tool. It's called Alea. It's based on previous Xenon 1-ton and M-ton tools, but now for the Savins discovery and for others, we'll use this, which is an open source tool that provides runner submitters for TOMC and profile construction. It doesn't include how to make your own signal models, so that's something you have to input. But otherwise, it has a framework to add your likelihood then to Alea, define the functions of the likelihood, generate data in a common form. And as a tutorial, it includes a full, quote unquote, simplified, but still quite fully featured liquid xenon TPC style likelihood with nuisance parameters for the ER, with WIMPs, with everything. It's great. And this is based, as I said, on xenon 1-ton and n-ton SR0 WIMP analyses with, I think by now, much improved maintainable code from what I sometimes committed. So definitely, if you finish all the exercise sessions, or if you're interested in looking into more details of how are these things done for mid-sized experiment, definitely have a look here. Try out the analyses. It's relatively easy to install. At least we've had one trial of that. And I hope you have a look. And that brings us to the end of today's lectures and the lectures in general. So, summary of today, we spent a lot of time talking about frequentist confidence and what frequentist confidence intervals mean, which is that they are, number one, they're a method to include a true signal 90% of the cases for every possible signal, which is another way of saying they're repeated hypotheses tests for all of these signals, and you exclude them if your p-value goes below 1 minus the confidence level of your confidence interval. We talked in particular about the profile construction, which is a way of computing these frequentist confidence intervals for the case where you have nuisance parameters and where you want to make a Feldman-Cousins interval, or Feldman-Cousins-like, because you have nuisance parameters, which is that you generate times C estimates of the distribution of your test statistic for all values of your signal, or for all values of your hypothesis test, and then you compare that to your likelihood. And then lastly, I mentioned a couple of tools. If you're especially interested, you can check those out. You can email me if you're interested in something. And that brings us to the exercises. Questions before that? Yes.
It's a bit technical, but since we have tools now for this extended likelihood that, like FlameDisk, I think LZ already explained this. What is stopping all of the experiments from using this extended likelihood?
So LZ is not using FlameDisk. LZ is using, or LZ is using the software framework FlameDisk, but it's not using that extended likelihood for their science results yet. Partially because you're looking at very few events and you're trying to validate a 6-dimensional model that's quite tricky. So what they are doing is during the development of FlameDisk, there was also developed a version of FlameNest that was very nicely featured. Nest is a model for the response of liquid xenon and the detector. And so that part was used to then, it's a combination of, it's a combination of what I showed you here, which is called Alea, with a template generation. So if you want to have something that both provides you the template generation and this inference framework here, then there is this FlameNest that has that kind of functionality. But yeah, I think at the moment, LZ and Xenon don't even agree on using Nest. So moving beyond that to using a 6-dimensional likelihood that it's very hard to validate, it's going to take some time.
So it's because we can't yet validate Nest.
Right, and second of all, well, no, I mean, Nest is fitted to data. Nest is definitely validated, but that's not the only thing that's been validated, right? Xenon has its own fast detector simulation that is also validated to its data. So this is more just people have different tools. But when it comes to FlameDisk also, there is a critical part here, which is the computation time still is just not feasible, right? You can't do this profile construction with FlameDisk. You can do it with FlameNest because there you just do the profile construction. You take a lot of times C's, you fill it into a histogram and you fit it, but you cannot do this full 6-dimensional thing because it's just not computationally feasible to do like 6,000 times C's times 20 WIMP masses times 20 signal sizes for each. It's just not something you can do within a reasonable time that will allow you to do an analysis. If we could speed up FlameDisk to the point where that were possible, I would expect that you would see more takeoff. But I think until that's the case, then people might not even spend a lot of time. Or, I mean, there has been a lot of clever people who have spent a lot of time making FlameDisk work well. And it does, but I think it's a hard problem. It's a really hard problem. It has promise for the future. I think if you have really big exposures, they show you if you can get it quite good performance out of it. But it's not something that's ready for like these kind of big times C productions.
Other questions?
Yes.
This is another technical question. So when you do a WIMP search with an get to go like this.
Mhm.
And then you have to drain it into you under fluctuation.
Yes.
What is the technical reason you have to do that?
Aesthetics mostly. I'm like, that sounds like a joke, but it's also a fair point. Now, why would you want to do that? You could have different reasons. No? So this is why these guys are lightly colored here, which is to say that below here, Xenon decided to set there what is called the power constrained limit, which is one of these alternatives to set these thresholds. Xenon set theirs at their median sensitivity. The argument for setting it there versus some other where is that you don't want a downward fluctuation itself to benefit your limit. Now that sounds a bit weird, right? We can get lucky sometimes. But the thing is, it might not be luck that makes you downward fluctuate. It could be that you overestimated your background, right? And then you compare that to a data set. The data set is true, but your model is not. Then you're going to induce downward fluctuations. And you'll then sort of artificially get quote unquote artificially good limits. Now when you do this PCL, I think it's best practice, and certainly the paper recommends also showing this, which is the unconstrained limit, which is then saying, okay, if you hadn't applied this, how far down would it have gotten? In this case, it's not so extreme, right? You wouldn't say, oh, they had a huge downward fluctuation, they probably have some problems that they're not able to characterize. But in other cases, certainly we have seen that these guys have gone quite far below. Again, what they did when they saw that was they did a lot of tests, right, and really tried to figure out what was wrong, you know, because it clearly is at least indicative of a background mismodeling. But as I said during the goodness of fit tests, unfortunately, many cases, the outcome of a goodness of fit test, you know, they're not conclusive always, right? They just say, yeah, you should keep worrying about this. I hope in many cases we do keep worrying about these things, but at the moment, I don't think that it's possible to go much beyond that. But in general, you know, that's at least one reason for doing it, is because you say, okay, I want to be not so sensitive to sort of mismodeling. I think that's the best argument. The other argument would be to say, down here I don't have sufficient, or down here it's really just statistical fluctuations, and I sort of on a gut level distrust statistical fluctuations to exclude WIMPs. I think the argument about sort of resistance against mismodeling is the best argument for putting some threshold there. Where you put that threshold depends a bit on, again, your preferences. I think it would be fine to put it at -1 sigma, which is something, for example, LZ did. But it's, yeah, that's the argument. And then in other fields, if you look at collider physics, they do something which is called CLS, which is then, instead of a sharp cutoff, it is a gradual sort of penalizing of your p-values as you get closer to more and more downward fluctuations. And in fact, it means that your coverage at your sensitivity is 0.95 instead of 0.9. Well, I mean, they have 0.95 confidence interval, so their coverage is 0.975, but wait, no, 0.975. But that's beside the point. Right, but there are these other ideas also for this.
If I may say it, probably, surely with less precise wording, what we are trying to do here is to avoid setting an upper limit down to a region where we don't have sensitivity to. This is basically, and then this can be expressed in a more precise way in terms of discovery potential and so on. But this is what you want to avoid, or what you want to protect yourself.
Right. And then I think a good point of that is, why would you be concerned about that, right? Because as we saw, like, coverage is not, right, an upper limit is a creature that is a random outcome, right? It has randomness to it, which means that you should look at them with the amount of reverence that is, you know, afforded to any object that was created through a lot of sweat and tears from a lot of people, but also be aware that these things should be held a little bit lightly, right? You shouldn't take these as statements of exactitude, right? These are uncertainty estimates. These are uncertainty estimates on your best fit, which is 0. And so I think part of the reason why we care about setting these thresholds is that people interpret them much more solidly than I think we should when we look at 90% confidence intervals, right? In 10% of the cases, the signal is above here, right? Or if the signal is above here in 10% of the cases, the upper limit is below. See, it's hard to talk about it in the right way. But that means that you shouldn't, right? You should never, or you should not immediately discount the signals up here. And you should not take a single experiment's upper limit as the final say about the existence or non-existence of dark matter, just because all of these are probabilistic statements. But because it's so easy to look at a line and say, oh, it's the line, then you have to sort of do a little bit of pre-digestion for people, because people are so willing to go and say, oh, this line means that this model is excluded. And when they say excluded, they don't take that coverage part with it. So then we sort of do part of the reading for them and make sure that we hide the limits that need that extra care from them, if you will.
The other nice statement that one can keep in mind when looking at this stuff is that any discovery is preceded by a worse upper limit.
Yes, also that is actually also a very good point. No, it's not a one-to-one, but it's nearly a one-to-one to counting sigmas. So if you have, so this is an one sigma upwards fluctuation, which means that, if I remember right, our p-values was around like 0.17 or something like this for this guy. So it's wait, 1 minus plus. Okay, never mind. But the point is exactly that. Marco is exactly right. That the worse your upper limits gets, at some point that turns into a discovery also. Yeah.
So if the signal is there at the beginning with a weaker detector, you will see just an upward fluctuation of your estimated background.
Yes. An upward fluctuation of your estimated background and a sharp upward fluctuation of archive submissions.
And then at some point you improve with your detector, you increase it, you reduce the background, and then it pops up.
Yes.
And yeah.
Right. And if you're impatient about that beautiful day, you can just do time series and look at beautiful results already.
So, hands on?
Yep.
Hands up?
Let's do stats.
Yeah. So another short motivational speech. Sooner or later, you will face these things. Probably at the end of your PhD, you have to face this stuff, and instead of putting it in a black hole or in a black box and crossing fingers and getting some numbers out, it's better at least to have a clue on what's going on. So you can use the opportunity here with the hands-on. You can profit of the various tools that Knut provided, both with the notebooks, but also with the link to the stuff, because this is very useful to go deep in it, die and resurrect with some knowledge.
Exactly. And even if you never do statistics yourself, if you're interested in where dark matter is, you'll look at these plots, right? And you should understand what they're saying to you, because they are saying something to you, but it's not just line above good or above bad or below good. No. Good.
Yeah.
Stats. I was just going to say, like, let's get now self applaud starting here.
Do you need to say something about the exercise, or are they?
No, I think I said everything I need to say about the exercise before. I will post a solution tomorrow, about like proposed solution tomorrow. Yeah, so today's is there, tomorrow there will be also for this one.
We have about half an hour.
Yeah.
Of hands-on.
Time to start. Perhaps not time. Yes.
Are these the notebooks in the Alea?
No, it's there in the agenda. 2 seconds. I'll be with you right after fixing something here. Let's leave this guy.